Traditionally, the greatest and most puzzling mysteries of the universe are tied to black holes, the Big Bang, or dark matter and energy. But no, not only those. In fact, the biggest mysteries of the universe are not hidden somewhere far away in space and time. They are already right here next to you. They are everywhere. While we sleep, they pierce our bodies by the millions. For more than a century, we have known about them, studied them, caught them, measured their energy, yet we are still searching for their sources. We fear them when we fly into space, and even when we board airplanes. And if we do not learn how to shield ourselves effectively from them, we can forget about our dreams of interstellar travel. Of course, we are talking about cosmic rays, whose nature we are going to break down in detail today. The astrophysics of elementary particles began on a balloon. In 1912, Austrian physicist Victor Hess carried out several flights funded by a grant from the Austrian Academy of Sciences. Naturally, he did this not just to enjoy the scenery, but with a clear scientific goal: to finally figure out the mystery of radiation. At that time, scientists were deeply interested in radioactivity, discovered at the end of the 19th century. They knew that some kind of ionizing radiation was affecting the molecules of air. In other words, something was knocking electrons out of atomic nuclei, ionizing the atoms and molecules present in the air. But what exactly was the source of this radiation? No one knew for sure. German physicist Theodor Wolff had developed a device called the electrometer, capable of measuring the rate of ion formation inside a sealed container. Many physicists used this instrument in their hunt for the elusive source of radiation. But the task turned out to be far from simple, because ionizing radiation was detected almost everywhere, regardless of the research site, whether deep underwater in lakes or atop high mountain peaks. The scientific community leaned toward the idea that the source must be the Earth itself, radioactive isotopes hidden in the Earth's crust, right beneath our feet. But Victor Hess wanted to test this hypothesis. He decided to measure ionization levels as high above the Earth's surface as possible. If the radiation really came from the crust, then with altitude, the ionization of the air should decrease. So, taking with him 3 improved versions of Wolff's electrometer, Hess conducted a series of balloon flights, during which he discovered something completely unexpected. On August 7, 1912, he ascended to an altitude of about 5,200 meters and measured ionization levels that turned out to be 3 times higher than on the ground. Thus, Hess realized that the penetrating radiation ionizing the air was not coming from below, or at least not only from below, but also from above. He ruled out the sun as a possible source, since during an almost complete solar eclipse, the radiation did not decrease. Therefore, the radiation must originate from some other cosmic source. And so, Victor Hess discovered cosmic rays, a breakthrough that earned him the Nobel Prize in Physics in 1936. First of all, it's worth noting that the word rays doesn't really reflect the essence of the phenomenon. The term cosmic rays has nothing to do with electromagnetic radiation like gamma rays or X-rays. But this wasn't known at the beginning of the 20th century, so the name stuck. In reality, unlike photons of different energies, the particles we call cosmic rays have mass. And what kind of particles are they? For the most part, they're just ordinary free protons, that is, hydrogen nuclei, which are abundant throughout the universe, drifting here and there. Each of them carries its own energy, meaning the speed at which it moves. And what we call cosmic rays are essentially protons moving at extraordinary speeds, sometimes coming frighteningly close to the speed of light. This makes them some of the fastest matter in the universe, carrying energies that the designers of the famous Large Hadron Collider could only dream of. Something out there in the cosmos accelerates subatomic particles, and that something is tens of millions of times more powerful than any accelerator on Earth. So, these high-speed atomic nuclei slam into Earth's atmosphere every single day, in numbers reaching trillions upon trillions. About 90% of them are protons, free hydrogen nuclei, but roughly 9% are helium nuclei, the so-called alpha particles. The remaining 1% are the nuclei of heavier chemical elements, essentially accelerated clusters of protons and neutrons. Of course, there are also electrons. One might expect them to be plentiful among cosmic rays, but in fact, their concentration is less than 1%. This is because electrons are much lighter than protons, making them easier to scatter during their long journey from the acceleration source to Earth. They interact readily with photons of the cosmic microwave background and lose their energy. Protons also lose energy this way, but not nearly as dramatically. It's also important to point out that both protons and electrons are charged particles, which means they interact with magnetic fields. This is why Earth's magnetic field serves as an excellent shield against cosmic rays, at least against most of them, especially those generated by the sun. Yes, our star, the sun, is the primary source of most of the protons and electrons bombarding Earth's magnetosphere. This constant stream of charged particles is what we call the solar wind. Sometimes during solar flares, the sun can accelerate particles to much higher energies. However, the term cosmic rays usually refers not to these solar particles, but to the much more energetic ones that manage to break through Earth's magnetic shield and are not connected to solar activity. These originate from beyond our solar system, and sometimes even beyond our galaxy, which means cosmic rays are a unique opportunity to study matter from the depths of outer space. Highly energetic atomic nuclei are capable of penetrating Earth's magnetic field, but then they face another obstacle, the atmosphere. And this barrier is much harder to pass through, as it is filled with a variety of atoms and molecules waiting to be struck. This is why cosmic rays rarely reach Earth's surface directly. Instead, their enormous speed, and therefore enormous kinetic energy, ensures that any atom or molecule they collide with is essentially doomed, ripped apart into fragments. These fragments, themselves subatomic particles, inherit momentum, get accelerated, and go on to smash into other atoms and molecules in their path. This chain reaction creates an entire cascade of secondary particles, each with lower energy, but together producing a kind of avalanche of interactions. A single high-energy cosmic ray can unleash a whole shower of subatomic particles and ionized nuclei rushing down toward Earth, an effect known as an air shower. The typical secondary particles produced in such collisions include protons, neutrons, electrons, as well as neutrinos, pions, muons, and high-energy photons. Some of these secondaries can reach the ground and be detected. For example, pions quickly decay, releasing particles such as muons, neutrinos, and gamma rays. Muons are particularly interesting. They are similar to electrons, carrying a negative charge, but they're slightly heavier. Because they interact less strongly with matter compared to pions, they can travel freely through the atmosphere, often making it all the way to the Earth's surface. In fact, the flux of muons reaching Earth is quite remarkable. About 1 muon per second passes through the volume of a single balloon. Before the first particle accelerators were ever built, it was precisely cosmic rays colliding with the atmosphere that allowed scientists to study elementary particles. In the 1930s, knowledge of atomic structure was still limited to protons, neutrons, and electrons. But by observing cosmic rays, physicists discovered the muon, and even the first known antimatter particle, the positron. In general, the number of secondary particles that reach Earth depends on the energy of the atomic nucleus that entered our atmosphere, and these energies can vary enormously. To catch the primary particles directly, detectors must be placed high in the atmosphere before the particles slow down and are destroyed by collisions. That is why instruments are mounted on high-altitude balloons, on satellites, and even on the International Space Station. The energy of cosmic rays is usually measured in electron volts. 1 electron volt, simply put, is the amount of energy that an electron gains when it is accelerated by an electric potential of 1 volt. In other words, if you take a single electron and accelerate it in a vacuum with 1 volt of potential difference, the result is 1 electron volt of energy. Scientists often use larger multiples of this unit, such as mega electron volts, which means 1 million electron volts, or giga electron volts, which means 1 billion electron volts. It is just a more convenient unit than joules when working with elementary particles. Most cosmic rays that bombard Earth carry energies between about 100 million electron volts and 10 billion electron volts. That corresponds to speeds from roughly 43% up to 99.6% of the speed of light. But sometimes particles appear that are accelerated to even higher speeds, carrying truly mind-boggling amounts of energy. The most powerful cosmic ray ever recorded struck a detector in Utah in the United States on October 16, 1991. It was moving at a speed extremely close to the speed of light. Its energy was so great that scientists nicknamed it the "oh my God" particle. To be precise, its energy measured 320 exa-electron volts. That is a 3.2 followed by 20 zeros. For comparison, this is tens of millions of times greater than the energy ever achieved at the Large Hadron Collider. Converted into joules, that is about 50 joules of energy. To put that into perspective, scientists often compare it to the energy of a baseball traveling at 100 kilometers per hour, or a bowling ball dropped from shoulder height. That may not sound extraordinary, but remember, all of that energy was packed into a single subatomic particle. As for what the particle actually was, that remains unknown. If it was a proton, then its velocity would have been incredibly close to the speed of light. So close that such a proton could chase a photon across the universe for years, falling behind only slightly. According to Einstein's special relativity, at that speed, the particle would also have experienced extreme time dilation. If it traveled for about 1.5 billion years in our frame of reference, then in its own frame of time, less than 2 Earth days would have passed. In fact, the "oh my God" particle appeared to violate the so-called cosmic speed limit, which suggests that particles should not exceed energies above roughly 60 exa-electron volts. Beyond that threshold, they are expected to interact strongly with the photons of the cosmic microwave background, the faint radiation that fills all of space. At near light speeds, those low-energy background photons appear to the proton as much more energetic radiation, effectively bombarding it and slowing it down. But not this time. The "oh my God" particle surpassed the theoretical limit by about a factor of 5. One hypothesis is that it was accelerated relatively nearby, somewhere within our local supercluster of galaxies, and therefore the background photons simply had not had time to slow it down. But to impart that kind of energy to a proton, nature would need an extraordinarily powerful astrophysical accelerator. And so far, no traces of such an accelerator have been found in that region of the sky. At first glance, you might think, if we just trace back where these particles came from, we could pinpoint their origin and finally learn what accelerates them. But it's not that simple, because they seem to be arriving from everywhere. The key is that cosmic rays are charged particles, which means they interact with magnetic fields. So on their journey to Earth, say from another part of the galaxy, they are constantly deflected by the magnetic fields of the galaxy itself, by the fields of other stars, by the fields of our solar system, and finally, by Earth's own field. By the time they reach us, their original trajectories are so scrambled that it is practically impossible to trace them back to their exact sources. And so, the question of what accelerates particles to such mind-blowing energies remains one of the toughest puzzles in astrophysics. Of course, it's easy to point fingers at quasars, gamma-ray bursts, or supernova explosions. After all, these are among the most powerful energy sources we know of, but proving this directly is extremely difficult. In fact, the very first confirmed source was identified only indirectly, and indeed, it turned out to be supernova explosions. This breakthrough discovery wasn't made by cosmic ray detectors directly, but thanks to a gamma-ray telescope in space named after physicist Enrico Fermi. In fact, Fermi himself, back in 1949, had already suggested what might be responsible for accelerating protons. He proposed that the highest energies of cosmic rays are achieved in the magnetic fields of interstellar gas. Over the following decades, scientists refined his model and showed that the real key to acceleration lies in the shock waves produced by supernova remnants. Even though the star itself has died, its clouds of gas and magnetic fields remain, and they can expand for thousands of years. The heated material rushes outward faster than the speed of sound, generating a shock wave that plows into the surrounding interstellar gas. The plasma from the supernova carries magnetic fields, and particles can be caught up in this shock front, riding along with it. Inside the magnetic field, the particles move chaotically, but every so often they cross the main shock wave. And each time they do, they gain an extra boost of energy, about 1%. After many such crossings, a particle can accumulate enough energy to finally escape the magnetic field and become a cosmic ray. Scientists confirm this idea by observing the remnants of supernovae IC 443 and W44. The key was not to look for the cosmic rays themselves, but for the traces they leave behind. When a supernova explosion occurs near a dense molecular cloud, the accelerated cosmic rays streaming out of the shockwave can crash into the cloud, producing a telltale signature of gamma radiation. This happens because colliding protons can create a neutral particle known as a pion. Pions are unstable and decay almost instantly, releasing 2 gamma photons, exactly the kind of signal a gamma-ray telescope can detect. The crucial point here is that gamma rays, unlike cosmic rays, are photons and therefore not deflected by magnetic fields. This means they travel straight from their source to us. And in 2013, the Fermi Gamma Ray Telescope managed to capture such gamma rays from supernova remnants. The energy of these photons matched precisely what would be expected from collisions of cosmic rays with matter. This confirmed that, at least in part, cosmic rays do indeed originate from supernova explosions. But here's a good question. Do all cosmic rays come from supernovae? Judging by the energies that supernova explosions are theoretically able to generate, the answer is no. The most energetic rays ever detected must come from some other source, something far more powerful. But what exactly that is remains unknown. Scientists believe that natural accelerators of ultra-high energy rays are unlikely to exist within our own galaxy, since such objects would need to produce energies on par with active galactic nuclei. That's why the most powerful cosmic rays are thought to come to us from beyond the Milky Way. The first solid evidence for this emerged in 2017, when scientists were finally able to confidently identify a region of the sky from which the largest number of high-energy particles seem to arrive. These large-scale studies are being carried out in Argentina at the Pierre Auger Observatory. This massive facility detects secondary particles, the very same air showers created when cosmic rays strike the atmosphere. The most powerful cosmic rays are extremely rare, hitting Earth at a rate of about once per square kilometer per year. To catch enough of them, the observatory spreads its detectors across an area of 3,000 square kilometers. It uses 2 types of detectors: fluorescence telescopes and surface detectors. The fluorescence telescopes photograph faint flashes of ultraviolet light produced as particle cascades pass through the atmosphere. Meanwhile, the surface detectors, large water tanks, pick up charged particles that create bursts of blue light when they strike the water, a phenomenon known as Cherenkov radiation. By combining both detection methods, the Pierre Auger Observatory can better track the direction in the sky from which the primary particles may have originated. And after 12 years of observations, researchers found that one region of the sky showed 6% more cosmic rays with energies above 8 exa-electron volts. Since this region is nowhere near the center of our galaxy, it strongly suggests that their source lies beyond the Milky Way. Of course, even at such high energies, the particles are still significantly deflected by magnetic fields, making it hard to pinpoint their exact origin. But the overall direction indicates an intergalactic source. The observatory is now being upgraded to catch even higher energy particles, which are less strongly deflected, and thus could finally allow us to trace their sources with much greater precision. Of course, when discussing this topic, we can't ignore the question of how cosmic rays affect our lives, because after all, they are a form of ionizing radiation. In other words, cosmic rays can knock electrons out of atoms, thereby damaging them. If that atom happens to be part of some electronic component, say inside a satellite, this can cause malfunctions in its systems. If instead the atom is part of a living organism, for example within a DNA molecule, then cosmic rays can damage tissues or even trigger DNA mutations. However, as we've already mentioned, most cosmic rays are deflected by Earth's magnetosphere, and the most energetic ones are absorbed by the atmosphere. As a result, only a small fraction ever reach the surface. They are simply one component of the natural background radiation we all receive throughout our lives. To be precise, cosmic rays account for about 11% of our total radiation exposure. So unless you spend your entire life flying on airplanes or living aboard the International Space Station, your body has nothing to worry about. Even in airplanes, the risk is relatively minor. The average annual radiation dose for flight attendants and pilots is between 2 and 6 millisieverts. A sievert is the unit used to measure ionizing radiation dose, and it reflects the health risk it poses. For example, A dose of 1 sievert corresponds to about a 5.5% increase in lifetime cancer risk. A fatal dose is typically around 4 to 5 sieverts. For comparison, according to the IAEA, the average person receives about 3.5 millisieverts per year. Airline crews only add an extra 2 to 6 millisieverts on top of that. Naturally, the International Air Transport Association carefully monitors flight hours and ensures that crew members do not exceed recommended radiation limits. The upper guideline is 20 millisieverts per year, much higher than what crews actually receive. But of course, things are very different for long-term stays in space. Astronauts aboard the ISS, orbiting 400 kilometers above Earth, receive more than half a millisievert per day. In other words, in just 12 days, they accumulate more radiation than an airline crew member gets in an entire year. That's why space agencies strictly limit the duration of astronaut missions, although some have still spent a year or even longer in orbit. It's worth noting that even the ISS is still a relatively safe zone, since low Earth orbit remains under the protection of our planet's magnetic field. The environment becomes much harsher when traveling farther out, say to the Moon, or even more so, to Mars. For example, had a major solar flare occurred during the Apollo missions, astronauts outside the shield of Earth's magnetosphere could have been exposed to lethal doses of radiation. A journey to Mars is even more dangerous in this sense, simply because of its duration. Even without taking solar flares into account, a mission to Mars poses a serious challenge to the human body. During the Curiosity rover's 253-day cruise to Mars, researchers measured how much radiation the spacecraft's instruments absorbed. They determined that under similar conditions, an astronaut would receive roughly 0.66 sieverts of radiation, raising their lifetime risk of developing cancer by about 3%. This wouldn't cause immediate sickness, but there's another concern: the potential effects of cosmic rays on the central nervous system. Some studies suggest that they could impair cognitive function, alter behavior, and affect overall health. Changes that could appear right away, not just years later. Of course, potential solutions exist. Engineers might one day develop powerful, compact magnets to deflect charged particles, or new shielding materials to line spacecraft hulls. Perhaps even specialized medications could help minimize radiation damage to astronauts. But for now, none of these solutions are ready, which means cosmic rays remain one of the greatest threats to humans in space, or on the surface of worlds with only weak atmospheres and magnetic fields. And remember, all this is happening while the true sources of the most energetic cosmic rays are still a mystery. They're bombarding our bodies right now. They're an inseparable part of our environment, and yet we still don't know what produces them. In the end, it shows just how far from complete our understanding of the universe really is.